Okay, welcome back, everybody. You record, okay. Okay. Welcome back, everybody. We continue with the final part of the mini course on nonlinear Grassmannians and fact manifolds, which will be presented by Stefan Haller. Please go ahead.
Thank you. Okay, good morning. Last time I mentioned that I'm going to show you a dual pair that's associated with contact manifolds, and during the first half hour of this lecture I will deliver and show you what we call the EP contact dual pair, because it's related to the algebraic equation on the contact group, the group of contact differentials. And during the second half of the talk I will show you infinite dimensional nonlinear flag manifolds, which are generalizations of the Grassmannians we've seen before, particularly in Cornelia's talk, and they are motivated by the considerations in this discussion. Okay, so last time we had the symplectification of a contact manifold. We call the symplectification of a contact manifold P can be identified using a compact form with the manifold P cross the reals minus 0. It's a symplectic manifold, and we looked at the contact group, group of contact differentials acting on this manifold, and it's acting in a Hamiltonian fashion, and we looked at the moment map and played around with that. And today I would like to replace this with an infinite dimensional analog in a very simple way. Rather than looking at points in P, we will fix a closed manifold S and look at the paddings of this closed manifold S into P. So we will replace the P with the paddings from a fixed closed manifold S into P. And rather than looking at real numbers, we'll look at infinity functions on S. In the real numbers minus 0. So this looks like an ad hoc naive replacement. This certainly is an infinite dimensional manifold. Cornelia explained how you put the structure of the Fresher manifold on the embeddings of the fixed manifold S and P. This certainly is an open subset in the Fresher space. So this is a nice infinite dimensional manifold. The group of contact differentials is still acting here. I will often write G for the group of contact differentials, the differentials on P that preserve the contact form. It's acting here, and to understand the action is it's probably useful to give a more natural explanation of the space that I wrote down here. Yes.
What goes wrong if on the right-hand side we would keep R without 0?
It's not going to be symplectic.
Also not weakly.
We will have a closed 2 form, but the closed 2 form is not weakly non-degenerate if you allow 0. This is what's going on. And the reason why we will take here.
I mean, if you don't take functions with, but just R without 0. You replaced R without 0 by these functions in that. So if you just keep R without 0,
then it's a very just a submanifold. I don't know if it's going to be symplectic, probably. But I'll give you a more natural explanation of the space I wrote down. This can be and should be thought of embeddings of the line bundle of densities on S. So this is a line bundle over S. And we look at fiber-wise linear embeddings into the, what was it? Into the dual of the line bundle L. That's associated with a contact manifold. We call the contact manifold the line bundle A. We associate with the contact manifold is just proportioned by the hyperplane field. And the space that I wrote down before, P cross R, this is just L star in a canonical way. So we are replacing L star by fiber-wise linear embeddings of this line bundle of densities on S into this canonical line bundle we have over the contact manifold. And on this space, the group action is obvious. The group of contact differentials acts in the fiber-wise linear manner on the total space of this bundle here. And so we can just compose in an obvious way. And if you use this identification here, uses a contact form, and it also uses a trivialization of the density bundle that is a density on S. So if you want to write down this identification, you need a contact form alpha such that the size the kernel of alpha, and you need a section, the density on S. So this is a section, lower vanishing section of the density of the density bundle. And then if you write down the action here, it's slightly more involved. It will involve a conformal factor that comes from the choice of alpha, and it will involve a conformal factor that comes from the choice of U. But now there's another group that's acting here too. There's a second group that's acting, the group of diffeomorphisms. So well, H for that, the diffeomorphisms of S is acting here too in an obvious way. The density bundle is a natural bundle over S, so the group of diffeomorphisms acts in a fiber-wise linear fashion on the total space of this line bundle. So you can compose from the right to act on the space of linear fiber-wise linear matrix. So there are two groups here acting in a very natural way, and of course the actions commute. One feature we had on the total space of L star, there was a canonical one form, and this canonical one form gave rise to the symplectic form. The same is true here. This infinite dimensional manifold here, it needs a canonical one form. So there's a canonical one form. No. What's this here? One form theta on this space, I will call it epsilon for embeddings on epsilon. And to write down a formula for this one form, it's convenient to think of epsilon as a subset of smooth maps from S into L star. So I'm just using a trivialization of this line bundle here to view epsilon as a subset here, because then you can just write down a one form by telling how it reacts to a tangent vector. Tangent vector is just a vector field along such an embedding, and what you can do is you just integrate. So you contract this vector field along S, you contract it with the canonical one form we have on L star. So these are maps into L star. We contract with the canonical one form we have here, and we just integrate against the density on S. Yeah, so this is a canonical one form on epsilon. It is invariant under both groups, G and H. So that's just like before, just infinite dimensional. Then on the symplectification, we looked at the differential of theta, and it turned out to be symplectic, and we can do the same thing here. If you look at omega, differential of this from theta and epsilon, this is now symplectic. Epsilon, to be more precise, it's weakly symplectic, weakly non-degenerate. You can write down a formula, it's straightforward to find formula. If you in this picture where we think of epsilon as subsets of maps from S into the total space of the line bundle. Two vector fields along such a map. They can be contracted with the symplectic form or the omega, those two form we have on the total space of L star. We can contract them again and integrate against the density. And then because of this formula, you see it's weakly non-degenerate. Weakly non-degenerate as long as you stay away from the zero section where omega fails to be zero. So this is why we remove the zero section.
So in L star you have to remove the zero section?
Yes.
Okay. The star is saying it's a dual, or it's saying it's
a dual line bundle.
Yeah.
The star is not, it's not denoting the removal of the zero section. Here it's the zero section is removed because I'm looking at embeddings which have to be fiber-wise linear and invertible, so fiber-wise non-zero. So it's automatically removed if I write embeddings here. But in this picture, in this way of writing, we have to remove it by hand. Okay, so it's symplectic, and we have the primitive, the theta, and even the theta is invariant. So the action of the groups, both groups will act in Hamiltonian fashion, and we will have two equivariant moment maps. The one moment map will take you to the Lie algebra of the group G. So these are just these are the functions on P, or can be identified with the functions on P. So the dual space of this. These are some distributional densities on P. This is where the one moment map will take us. This is the left moment map, and I showed you that yesterday. It's going to be equivariant, and explicit formulas can easily be written down. Let me do that. So this moment map applied to such a pair, so that we have an embedding phi and the function h. And this turns out to be you push forward h times mu. So mu is the density on S. You weigh it with the function you have here, and then you push that forward to obtain a distributional density of P. So this again involves the mu, and this is because there's some this moment map is equivariant. Then the other moment map that comes from the action of H, that will take us to the Lie algebra of the Lie algebra of the differential group of S. So these are just vector fields on S, dual. So these are some distributional vector field densities, but we will actually end up in smooth word forms up to some identification again that involves the choice. So this is the right moment map, and an explicit formula for that would be you pull back the contact form using your embedding, and you multiply by H. So these are explicit formulas for the moment maps.
What is H now?
Phi and H is a pair here, like an embedding and a function of S that we can. Okay, so it's very, very natural picture that generalizes the symplectification. And actually, you can recover the symplectification by putting S a point. If you choose for S a point, then you recover exactly the picture we had the other day. Okay. So we started that, and the first observation here is a theorem we obtained together with Cornelia Wiesner. This space epsilon with these two actions here actually forms a symplectic dual pair. In the sense of Weinstein, or more precisely, the orbits of the two actions are mutually symplectically orthogonal to each other. So two orbits through a common point, an orbit of the group G and an orbit of the group H, if at a common point, the two tangent spaces we have there are mutually symplectic orthogonal complements from each other. Of each other. The strongest version of symplectic dual pair we have in each dimensions, like Cornelia mentioned the other day. So epsilon is a symplectic dual. This is not so hard to show. This is an infinitesimal statement along certain submanifolds in P or submanifolds in N star. You just work a little bit. This is not so hard. Once you have a symplectic dual pair, then you would expect that the one group is acting sort of transitively on the fibers of the other moment map. because that's what the being a symplectic dual pair means, at least in an infinitesimal formal way. And so we tried to make that more precise. The first thing we did is we looked at the levels of the right moment map. And it turned out that all levels of the right moment map are indeed submanifolds. Smooth submanifolds in the strongest sense you would wish for. They are smooth submanifolds that admit a complement locally. The splitting submanifolds. The levels submanifolds in the best sense, smooth and splitting. For each one from row we pick on S. So that's nice. The proof here does not use an infinite dimensional inverse function theorem. It's more in the flavor of the Weinstein chart, construction of the Weinstein chart I showed you yesterday. It's like finite dimensional contact constructions using tubular neighborhoods and some other ad hoc constructions. You can write down a trivialization. You can write down a local chart where these subsets become flat explicitly, more or less explicitly using the finite dimensional implicit function theorem. Well, and then the dual pair tells you that the group, this is the contact group here, should act sort of transitively on this level sets. And this is true. It does indeed act locally, transitively. Even better, the group action admits a local section, or admits local sections. So the action of the group contact differentials on a level epsilon rho. This is what I'm going to denote the levels. The action on a level admits local smooth sections. That means the orbit map from, so you fix a point in your manifold where the group acts, then you have an orbit map from G into the manifold given by acting on this point. And this map admits a local right inverse. So given any point in the neighborhood of the point you started with, there's a smooth way of picking a group element that will take you there. This is a very strong statement of local transitivity. That gives you immediately tells you it's locally transitive, it's infinitesimal transitive, and you can locally trivialize the orbit map. The orbit map will be like a fiber bundle, locally trivial fiber bundle. You do not get any information about the fiber level. But this is kind of the strongest thing you would hope for. And again, here too, the proof is finite dimensional contact geometry, very much in the flavor of the Weinstein chart. And then, well, if the group acts nicely here, transitively, you wonder about the isotropy group. Maybe we can write it as a homogeneous space. How nice is the isotropy group? And it turns out that the isotropy group is as nice as you could wish for. It's going to be a Lie subgroup in this infinite dimensional group of contact differentials. The isotropy just write G phi is a Lie subgroup. G is a group of contact differentials. And the isotropic group is a Lie subgroup for each phi is a Lie subgroup in the strongest sense. It is a splitting submanifold. It's a submanifold that locally admits a complement. So in particular, it's an infinite dimensional Lie group itself. So that means that you can regard the level sets as homogeneous spaces of the group of contact differentials. There's really the orbit map really is a locally trivial principal fiber bundle in the smooth category. The Yeah, so you can regard those as homogeneous spaces. So the levels of the right moment map are very nice. So that, what about the levels of the orbits of the other group action? The orbits of the other group action are even nicer and easier to understand. The group of diffeomorphisms acting here, and in the first factor we already have embedding. So here the action of TFS is free. This is why I restricted to embeddings, so that the action of TFS becomes free. So it's acting freely, and in fact we can mod it out and pass to the unparameterized version. And this will be Grassmannians. This is why I'm picking a G, letter G to denote that. So the action is free. This is the quotient space. What is it here? More explicitly, we get. Well, this is a submanifold of P, the image of the embedding we have, together with some decoration, with some structure that we call it gamma, that we get from this function, and that forces you to think a little more natural, think in this picture, and then it's rather clear that the gamma just is a section of this canonical line bundle L star we have restricted to our submanifold times tensorized with the density on N. So these are section of a line bundle along N, and the line bundle is just the line bundle on P we have restricted to N tensor product with the densities on N. This is what you get if you follow the factor out the group action and look at the unparameterized version. So these are submanifolds with some decoration. The decoration is essentially function, but not quite. It is a section of some line bundle. So these are decorated Grassmannians that pop out here by natural. And the first question you might ask is, well, how nice a map is this quotient map here? And it turns out to be a principal fiber bundle. This is going to be a difference principal fiber bundle. In fact, the quotient here, G, is a smooth, infinite dimensional smooth manifold. This is a Francesco manifold here, and that's not hard to see because you can project out the submanifold you have and forget about the decoration. That will take you to the Grassmannian tornado I talked about before, and you can do the same thing here. Forget about the function and just look at the embedding. That's the P. Sorry, thank you. And it is well known, it's a basic fact due to Peter Michel in the general setting, but in the compact case it's due to I forgot, sorry. Beans and Fischer. In the case we're leading here, that's a closed manifold S. It's Beans and Fischer in general, it's due to Peter Michel. That this map from the embeddings to the Grassmannian is a principal fiber bundle. And using this fact, you just add the decorations. You easily see that this is a principal fiber bundle. So this map is nice, and you can even like now restrict. You know that the moment map is invariant under the right group action, so the moment map is going to descend to map here, and here is going to be injective, and so it's going to parameterize some orbits because it's of course still equivariant. So this is nice. Well, if you notice dual pairs, the next thing you might want to do is to do some symplectic reduction. And the nicest level to reduce that is 0. In this case, you take the level 0. So these are the so what does it mean? The level 0, that means the moment map, we call the moment map, just essentially restricts the contact form to the submanifold. And that if that is 0, then that just means we have an isotropic submanifold. So the level 0 consists of isotropic submanifolds here, with some decoration, with some weight, the same weight. And the corresponding unparameterized version consists of, so these are isotropic embeddings, the unparameterized version are just isotropic submanifolds with some decoration. So it's just the same thing we've been writing here on the right-hand side, just n is assumed to be isotropic. And then, well, you might ask how nice a manifold is the subset of isotropic embeddings with decoration. And the answer here is nice again. This is a smooth submanifold here, and this is a smooth submanifold. And one way to see that is that to project out, as before, just the Grassmannian, forget about the decoration, then you end up in the Grassmannians of P, which are isotropic. So these are isotropic submanifolds. And then you can use the normal form of the contact structure near isotropic submanifolds to show that this here is a submanifold, a smooth submanifold. And once you know that, because it's a principal fiber bundle here, this is going to be a smooth submanifold. So that works fine too. So this would be the reduced symplectic manifold we get by reducing at 0. It is indeed a symplectic manifold. This follows from the fact that it's a dual symplectic pair. If you restrict the symplectic form here, it will, to the isotropic embeddings with decorations, it will have a kernel, and the kernel will be precisely the vertical part here. So it will descend to the base and it will define a symplectic form of the base. And if you look at the moment map here, it'll be injective, and it will, because of the equivariance of the moment map, it will take the canonical symplectic form we have on the corresponding coadjuvant orbit to the reduced symplectic form we get from epsilon. So let me wrap that up a little bit. Reduction at 0. Smooth submanifold. We have a symplectic, reduced symplectic one. The moment map. This moment map. This one is a canonical symplectic form. We have then the corresponding coadjuvant orbit with this reduced symplectic form. No, it's the red chalk that's here. It's totally soaked. I'm fine. Thanks for your concern. So so far the reduction is good. So what about the group action? How transitive or how well does the diffeomorphism group, the group of contact diffeomorphisms act on this space? Does it act transitively? It should act transitively. This is what the symplectic dual pair property gives us, at least in an infinitesimal way. But is that true? And is it how well do we understand the transitivity? And here the fact we can prove is again the group of contact diffeomorphisms acts on this space of isotropic weighted submanifolds in such a way that it admits smooth split local smooth sections. So again, the action is as locally transitive as you would like it to be. We even have local smooth sections of the action here. In particular, you can, yeah. Yes, that is not hard at all. I did not comment on that, but that is really the easy part. That's not hard. Because if they have the same isotropic, the same image, that means these are like this distribution, the same distribution. So in particular, their singular support has to be the same. That means the underlying manifold has to be the same. Then you have to just think about the weight. But it's really easy to verify that the weight has to be the same too. There is one caveat here, though. The isotropy group here, we cannot show that the isotropy group is a Lie group. So this is an open question. We tried in vain. The isotropy will be the group of contact diffeomorphisms that fits such an isotropic submanifold with its weight.
Excuse me, I think Peter has a question.
Yes.
Yeah, sorry, but it just fits now. I have two questions. The first one is, from the point of view of continuum mechanics, could S have boundary?
I don't know, Peter. I did not think about that. It's conceivable.
Yeah, so if you move a continuum, then I mean, continuum should end somewhere. And my second question is, co-adjoint orbits are via Kirillov connected to representations, unitary representations. And there is a paper by Gelfand and Werschig where they also have some structures to construct quite complicated and large unitary representations of diffeomorphism groups. So is this Kirillov way from co-adjoint orbits to unitary representations, could this be done in this setting?
Apparently it can be. Cornelia is working on that. I am not into that. I do not know the results there, but that's exactly what they're doing. They're trying to generalize this Kirillov construction to the co-adjoint orbits here. That's, I think, Cornelia and Hermann made.
No, not in the contact case.
And not in the contact
case.
case.
The volume preserving.
For the volume preserving diffeomorphism. It was
the part that I
yeah, so apparently there's some things can be done, but unfortunately I'm not able to see them.
Okay, thank you.
Okay, so the moral message is reduction at zero works extremely well with one caveat. And the caveat is that the isotropy group is not a Lie group. Even though you can, like, the orbit map can be locally trivialized, but only in the sense of Fröhlicher spaces, where you put the Fröhlicher structure on the fiber, the Fröhlicher structure on the isotropy group, then it can be locally trivialized. But what you really would like to have is a smooth Lie group structure here, and that we could not do.
So what was wrong?
It's just if you, this condition here, fixing, preserving a submanifold and the weight is not very nicely compatible with the chart I showed you last time. The chart for the diffeomorphism group. If you look what that condition means in this chart, it's I do not see that this defines a like nice smooth submanifold in the modeling vector space.
But it's automatically a group, right? By definition.
Yes, it's a group.
Yeah. But the problem is the smoothness. Yes.
Yes, can you model that by can you write down charts for this such that it becomes a smooth Lie group?
And in the sense of this topology,
Yes, even in the sense of vertical spaces, you can deal with that. So you know what the smooth curves are, you know what the smooth functions are, then you can play around, but this is not very substantial, I would say. But you can still make statements. But the other condition where we were here told you that isotropy is a Lie subgroup. If we look at the diffeomorphisms that preserve the embedding and the weight. So these are diffeomorphisms which like fix the points on the submanifolds. Each point here just the whole submanifold has to be preserved. They might move around points in the submanifold. For the embeddings, it has to fix every point of the submanifold, and it has to fix the weight. And that can be interpreted very nicely in the chart. That just means these correspond to functions on P whose one jet vanishes along the submanifold. This is a very nice condition, a linear condition in the chart. So this is why this is a Lie subgroup. But this condition here is not so nice, and I do not see how to prove that. Okay, so reduction at zero works like almost as good as you would wish for. However, if you do reduction at more general levels, it becomes very, very delicate, and the smooth category apparently is not the right category to deal with these spaces. So everything, lots goes wrong. If you look at a more general level and do reduction, then you would look at the level and mod out the stabilizer of the row. That would be one way of looking at the reduced space. Another way of looking at the reduced space would be you look at the pre-image of the whole orbit and mod out all of PDEs. These are two ways of understanding the symplectic reduction. And there's a canonical bijection here, it's a continuous bijection. But in general, even for nice row, in general, this is not a homomorphism. So these two descriptions differ in general. We constructed a counterexample here. It's not very complicated. But many other things go wrong. The orbit of rho, the coadjoint orbit of rho, this is a one form on S. If you move the one form with the diffeomorphism group of S around, the orbit, you don't expect the orbit to be a nice submanifold. Or the stabilizer of a one form. All diffeomorphisms on S that stabilize a one form, even if it's a contact form. You cannot expect this to be a nice group. Yeah, and many other things you might want to happen do not happen in general. Even if the row is a contact row, which is sort of like the nicest next level, you would like to reduce that. So it's very delicate, and the smooth category is apparently not the right way to describe that. But for zero level, the picture is rather nice, and I would conjecture, or I really expect that this is a Lie group. Just I was not, or we were not able to do it. Time's flying. How much time do I have?
Until 35.
35, thanks.
The homomorphisms which fix and then itself without the mu and the easier to fix.
So in this case, if you drop, so preserving the embedding but not necessarily the weight is actually not such a nice condition, because in this Weinstein chart, that means you're looking at functions whose one jet along like almost vanishes, but like all but one component of this one jet have to vanish along n. So this is not such a nice condition, as if you include the weight, then the one jet along the submanifold has to vanish completely, which is not much nicer. And here, if you drop the condition on the weight and look at the contact. Yeah, if you look at all diffeomorphisms that preserve a submanifold, you can easily write down a chart, such that in this chart, you see that it is a Lie subgroup. That's easy. It's just this Weinstein chart is not compatible with this construction. Okay, so now I could. Yeah, I intended to talk about linear flags, but that's not going to happen. So I intended to tell you about how this dual pair can be used to try to understand singular solutions of the geodesic equation on the contact group. So the geodesic equation on the contact group has been studied by Ewing and Preston, and among other things, they proved that the geodesic equation there is well posed, so that they have like short time existence and uniqueness for sufficiently small initial data. And they also laid out a plan how to construct, what singular solutions should look like, Picon solutions. And you can use this dual pair to make parts of this program rigorous. However, we cannot solve an equation here. Just if you could solve another equation, then you would get the Picon solutions. Another equation on this space epsilon. Hamilton equation. Because of time constraints, I would like to leave it there and not elaborate on that, and talk a little bit about infinite dimensional flag manifolds, because this is in the title, nonlinear flag manifolds. So it's motivated by the business here. The point is that these Grassmannians with decorations via the moment maps give distributions on the manifold, which are sort of like in the dual of the Lie algebra. And it's rather obvious to try to replace the Grassmannians by flag manifolds in order to describe more general, more singular distributions and still parameterize them in a smooth way. So this is what I would like to explain a little more carefully. What we're interested in, non-linear flag manifolds. These are just sequences of submanifolds, N1, N2, and so on, sitting in N. And we fix the type, so we fix the type N1 is supposed to be diffeomorphic to S1, and R is supposed to be diffeomorphic to SR. And we look at the space of all these nested sequences of submanifolds with fixed type. That really generalizes the Grassmannian, and we hope we aim at describing distributions on M whose singular support is contained in NR, but then there's a more singular part that's contained in NR minus 1 and so on, and the more singular part whose support is contained in N1. And it will turn out that this is a smooth, nice smooth manifold, and if you put weights on that, then you can actually parameterize you can parameterize very nice distributions in a smooth way. Okay, but to start with, we just look at set theoretically here is nested sequences of submanifolds, and we like to turn that into a smooth manifold, fresh manifold. So you can wonder if that is a submanifold of the product of Grassmannians. Certain subset in the product of the Grassmann manifolds. We know that the Grassmann manifolds here are freshly manifolds. So is that a smooth submanifold here? And the answer is yes. It's not particularly hard to show that this is a smooth submanifold. Then there's a parameterized version of that. We had that before. We had the Grassmannians, the unparameterized submanifolds, and we had the embeddings, which are parameterized submanifolds. And there's a parameterized analog here. We call it frames. Certain type S1 to Si, and these are just embeddings, collection of embeddings, phi1, phi r, product system embeddings, such that their images are contained, are nested like here, such that the image or phi I of Si is contained in phi I plus 1 Si plus 1. So this is the parameterized version, and obviously there's a map going from here to here that forgets the parameterization and just looks at the image. Picking from here to here. The fiber is just the group of diffeomorphisms. You reparameterize each Si, so this structure here. Group you factor out is the product of the diffeomorphisms of Si. And then you wonder, well, can we turn this into the smooth manifold such that this becomes a principal fiber bundle? And the answer is yes. And the answer is yes, because we have principal fiber bundles over the Grassmannians. I mentioned that before, the embeddings from Si to M form a principal bundle over the Grassmannians. And of course, you can take the product and you get a principal fiber bundle that now has a structure group. The products of these diffeomorphism groups. And this is obviously contained in here. These are certain embeddings which are nested. And because this is a submanifold and because this is a principal bundle, you automatically get for free that this is a smooth submanifold and this is a smooth principal fiber bundle. Yeah. So in this way, you can equip the space of nonlinear flats with the structure of a Fréchet manifold and just observing that this is a smooth submanifold in a Fréchet manifold. And similarly for the parameterized versions, and you have a fundamental frame bundle, which is as nice as you would like to.
We have another question from Peter Michor.
Yes.
Yeah, because it fits just here. How essential is it that the submanifolds are nested? I mean, you could have them not nested, and by specifying the intersection type. So if you have some.
Yeah, that's one thing we had in mind and never pursued. The reason to have some conditions on them is so that we still want that the group of diffeomorphisms of M to act transitively or as transitively as possible.
Mm-hmm.
So
but you could keep that if you have a transverse intersection or clean intersection in the sense of Einstein and so on. And probably this gives you all co-adjoint orbits.
No, all co-adjoint orbits, you just take any distribution and move it around with.
Yeah, sure.
It's very exotic. But you're certainly right. I totally agree with this statement. You can look at the transversal intersections and we've not pursued that though.
Thanks.
Okay. Yeah, well, there are other ways to describe the smooth structure here. There are two other ways you can try to put smooth structure on the flag manifolds. One would be, let me start with the frames here. It's really very straightforward to identify the frames with just embeddings of S1 into S2, plus embeddings from S2 into S3, and so on. Embeddings from SR minus 1 into SR, plus embeddings SR into A. Just by First, you take phi1 going to M, then you take phi2 to go back to S2. So there's a canonical map you can write down here, and this canonical map is in fact a diffeomorphism. So that's, I would say, quite different way of putting a smooth structure on the frame bundle, but it's the same smooth structure. You can prove it's a diffeomorphism, so it's the same smooth structure you get from the submanifold structure. And you can do that in the unparameterized way too. For the unparameterized case, so for the flags, you can write the flags sort of like a product. It's not going to be an honest product, it's going to be a twisted product of Grassmannians. And you can use that approach too to put a differentiable structure on the nonlinear flag manifolds in an inductive way. And it turns out to be the same smooth structure. So we can understand the nonlinear flag manifolds as twisted products of Grassmannians, and this way we obtain the same differential structure. And then the third way you might want to understand these flag manifolds is by the action of the group of diffeomorphisms M. Everything is diff M equivariant. And act with M, these conditions are obviously preserved by the action of the diffeomorphism group. And you can ask how transitive the action is on the flags. So you can look at the action of the group of diffeomorphisms on the flags here, and you can show that the action is locally transitive. Even more, you can show that the action admits local smooth sections. And so in particular, the orbits are open, and you can look at the isotropy group, and you can prove that the isotropy group is a smooth Lie subgroup in all diffeomorphisms, and then put them together, you see that you can understand the space of nonlinear flags as a homogeneous space of the group of diffeomorphisms on M. So you can understand nonlinear flags in some orbit under the diffeomorphism group can be understood as a homogeneous space of the group of diffeomorphisms mod the isotropy group. These are the diffeomorphisms which preserve this flag. So the action admits local sections. You can locally trivialize the orbit map. The isotropy group is a Lie subgroup, and so this is really as nice as we would like to have. So that's a third way of putting a smooth structure on the flag manifold. And it's the same because of this diffeomorphism here. So there are three ways you might want to put the differentiable structure on the space of nonlinear flags, and they all coincide. So this is kind of nice. So the last 5 minutes I'll show you why we are interested in that. The interest comes from parameterizing distributions, nice distributions, and parameterizing them by manifolds. The daily example would be you look at the Dirac deltas on the manifold M. You can parameterize them with by a smooth manifold. And this is slightly more elaborate. We can use these flag manifolds with weights. So we look at nonlinear flag manifolds. Consists of a nested sequence of submanifolds. Equipped with weights, each submanifold gets a weight. We call it mu1, mu r. And this is just a density on something that can be integrated against the function. This can, now what I told you, can be used to put a smooth structure on this, because this is just associated to the frame bundle. Look at the frame bundle. And you associate by the structure group, which clearly acts on the densities. An obvious way to write this set here as the underlying set of an associated bundle, and because this is a smooth manifold and principal bundle, this inherits a smooth structure. So this object here inherits a smooth structure by the story I told you before. And what is this good for? From this set, you have a function that takes you to C infinity. To the dual space of the functions. So these are these distributional densities. By just taking such a nested sequence with weights, you evaluate it against the function. Well, you do the most obvious thing you could do. You take the function, you multiply it with the weight on the submanifold Si, and you integrate over Si, and then you sum over all the R. So this defines a distribution on N. It has singular support NR, but on NR itself it's not smooth. There's a submanifold NR minus 1, and along the submanifold NR minus 1 it is singular too. It's even single here. Well, this is the distribution here. Think of, so we have a set of very nice distributions. I mean, the singular supports are still like submanifolds, and the longer submanifolds it's kind of smooth. And these distributions can be parametrized by this nice infinite dimensional Francesco manifold. This is why we are interested in this manifold, in order to parameterize these distributions. And the function space appears as the dual as a Lie algebra of the Hamiltonian group or of the contact group. We've seen that, and you can put other weights in order to obtain the dual of other Lie algebras. For instance, yeah, maybe I'm not doing that. Maybe show you one application we had of that. We looked at the Hamiltonian group, and we looked at flags. Manifold, symplectic manifold M, and we restricted to symplectic flags where the condition is that each submanifold is supposed to be a symplectic submanifold. This is an open condition, so this is an open submanifold of this infinite dimensional flag manifold. And the group of Hamiltonian diffeomorphisms acts on here in a Hamiltonian fashion, and it has a moment map. We'll take it to the dual of the Lie algebra, and the action on the symplectic flags is locally transitive. So this will connect the components of this space here with parameterized coadjoint orbits of the Hamiltonian group. And the moment map here is just what I wrote down here. U. So J on such a flag. You integrate, you have to evaluate against the function. And you just integrate the function against the corresponding power of the symplectic form on M. We integrate that in this sample. So it's a map that very much looks like this here. And there are yeah, so this is the first precise result we have. In this case, we can use this space to describe other coincident orbits of the Hamiltonian group that have not been described. Before. So yeah, but the main motivation is we would like to look at a very nice space of distributions and parameterize it by a smooth manifold. And this is what these decorated flag manifolds will do for you. The singular support is very nice. The wavefront set is very nice because it's smooth along the submanifold, but then they're still nested and there are more singularities. Okay, so thank you for your patience.
Thank you, Stefan, for the talk. We are ready now for questions. We're going to start with online questions, if there are any.
Yes, I think Peter Mayhor has a question.
Yeah. So this is again a very vague question. So if you take Sn as the boundary of the ball Bn+1, and you look at the diffeomorphisms of Sn modulo the subgroup of diffeomorphisms which extend to diffeomorphisms of the ball, you get a group which is called gamma n. This group parameterizes exotic differentiable structures on Sn+1 by using representations of each element in the quotient as a gluing map along the equator to glue north and the south hemisphere. Now, with this setup, if you just have one submanifold S, which kind of cuts M into two parts, so suppose it's codimension 1, so it cuts M into two parts, and then you look at those diffeomorphisms of S which extend to one of these parts, restrict it back, look at the quotient. Maybe you can mimic construction of exotic differentiable structures on M. And I think the transitivity of diff M on the flag manifold, the corresponding flag manifold, and not the infinitesimal one, but the global transitivity of diff M could play some role here or parameterize the whole thing. This is just what came to me when listening to your very clear and very nice lecture.
Thank you. The global transitivity is, we did not treat it at all because the methods we're using do not allow anything more than local transitivity. I totally agree that the global transitivity is a very interesting aspect, but we certainly need completely different methods to tackle that. Yeah, it sort of feels discrete what's left. If you can deal with the local transitivity and understand that well, and then just look what's lacking to understand the global transitivity, it's something discrete that's left, like the exotic structures there on the spheres, and then these methods of like using calculus to understand that. I don't see how they can help here. It seems like really hard questions to prove that the group would act transitively.
Yeah, one first example would be a torus, which cuts the one-point compactification of Rn into an inner solid torus and an outer solid torus. and try whether this gives new exotic differentiable structures on Sn+1 or I don't know. This is just vague ideas. Sorry for asking.
Yeah, the exotic structures on the spheres are understood by Mina and Kavya. I think that's very
Each
clear.
one.
Hmm?
Each one. I mean, I don't know whether. I mean, the Milnor construction is just using the equator, but if you use an embedded torus, I don't know.
But it's more like classifying H cobordismal classes, I think. There's a classical paper in the Annals by Milner and Kavya, if I'm not mistaken. And the number of different exotic differentiable structures related to Bernoulli numbers.
Okay.
I don't know if it's how explicit it is and if there's anything left.
Okay, well, if there aren't any more questions online, we are gonna end now and go for the lunch break, and
Awesome.
you people can talk during lunch.
Thank you.